Okay, I'd like to take a look at another problem where we're given a function and we're supposed to figure out where that function is increasing, decreasing, where we figure out where it has its maxima and minima, concave up, concave down, points of inflection, intercepts, asymptotes, and then based on all this information, we sketch a good graph. Again, I'm going to give you a rational function. So f of x equals x minus 1 over x squared, and that of course is y. Y is always equal to f of x. And let's start with a and b. We know that a and b have to do with the first derivative. And eventually we'll come to c and d, which of course have to do with the second derivative. Let's begin by taking the first derivative of this function. We're going to need the quotient rule because we have a fraction. So f prime of x equals the quotient rule. We put our bar down. Derivative of the top, derivative of x minus 1 is just going to be 1. Derivative of x is 1. Derivative of minus 1 is 0. We write the bottom exactly as it is. Minus the top exactly as it is. X minus 1 times the derivative of the bottom. Derivative of the bottom is just 2x. All over the bottom squared. So that's x squared squared. Let's go ahead and do some simplification there. So we have x squared minus x times 2x, so minus 2x squared. Minus minus is plus. 1 times 2x is 2x, so plus 2x. All over x to the fourth. And we can simplify the top. X squared minus 2x is minus x squared. So minus x squared plus 2x, or I could write it as 2x minus x squared. It's up to you. You could write it as x squared plus 2x if you want. Sorry, you could write it as minus x squared plus 2x all over x to the fourth. And we'll simplify this a little bit now so that when we take the derivative later, we take the second derivative, it'll be a little bit easier for us. We can factor in x out from the top. So 2 minus x to the fourth. We factor in x out from the top. We can cancel this x with one of these to end up with 2 minus x all over x cubed. And I think that's about as simple as we can get that. So let's go ahead and put our sign chart over here. So this will be our sign chart for f prime. I will clearly mark it as f prime. Minus 1, 0, 1, 2, 3, 4. And let's figure out where our first derivative is equal to 0, where it's undefined. So we can set f prime equal to 0. Fraction is equal to 0, where the top is equal to 0. So 2 minus x is equal to 0. X is equal to 2. So we have a 0 at x equals 2. And if f prime is undefined, then the bottom is going to be equal to 0. In other words, x cubed is going to be 0. In other words, x is going to be 0. So it's undefined. At x equals 0, we'll have to make a point, a mark there that looks different than a 0. It's going to be a u. And that breaks the real number line up into 3 parts. We can pick a point from each part. So let's say f prime of negative 1 is equal to, we're plugging everything into f prime right now, so it's 2 minus negative 1 all over negative 1 cubed. The top is going to be 3. The bottom is going to be negative 1. We don't really care. I mean, that's minus 3, but the important part is that it's less than 0. So it's negative over here. And if we plug in, say, 1, f of 1 is 2 minus 1 all over 1 cubed. The top is positive, the bottom is positive. That's positive. So it's positive over here. And if we pick a point to the right of 2, how about 3? F of 3 is equal to 3 minus 1 over 3 cubed. Top's positive. positive, bottom's positive, that's greater than 0. That's positive. It's positive over here. And we can put up and down arrows over our first derivative because our first derivative tells us where we're going uphill to the right and where we're going downhill to the right. So we are going, sorry, this isn't 3 minus 1. This is 2 minus 3. So 2 minus 3 is negative. So this is equal to negative 1 over 27. That's negative. Sorry, these should be minus signs. But anyway, we're going downhill to the right here, uphill to the right here, and downhill to the right here. Now that I have all my signs right. I'm just going to rewrite my first derivative over here to keep it safe. So f prime of x is equal to 2 minus x over x cubed. And now that I have that, since all this information that I worked out over here is encapsulated in my first derivative sign chart, I can get rid of all this. You can always pause and back up if you have to. But I am in a position to answer A and B now based on the information in my sign chart. So intervals where the curve is increasing and decreasing, so it's increasing from, looks like from 0 to 2, and it's decreasing from negative infinity to 0, and also from 2 to infinity. And we're supposed to find and classify critical points. So we see a critical point at x equals 2. It looks for a second like we might have another critical point at x equals 0, but we notice that the function, the original function, isn't even defined at x equals 0. So that's not a critical point. The only critical point we have is at x equals 2. So we have, you can see what kind of critical point it is. We're going up and then down. That's got to be at the top of a hill, so we have a relative max. Of some y value at x equals 2. We can go ahead and figure out what that y value is. So x and then y is always equal to, we plug the x into the original function. If I plug in x equals 2, I get y equals 2 minus 1, that's 1 over 2 squared, so that's 1 over 4. So 0.25 if you like. If you don't like fractions, instead of writing 1/4, you can write 0.25. That's the height that that function has at x equals 2, and that's at the top of a hill. Let's go ahead and do C and D, which we know involve the second derivative. I'm going to recopy the first derivative over here. So f prime of x is equal to 2 minus x over x cubed. So f double prime of x, we will need the quotient rule again. Derivative of the top, derivative of 2 minus x is going to be negative 1. Write the bottom exactly as it is, x cubed, minus the top exactly as it is, 2 minus x, times the derivative of the bottom, 3x squared, all over the bottom squared, so x cubed all squared. However you do the product rule, low d high minus high d low over square what lies below, whatever mnemonic you use to remember it, make sure that you get it in the right order. Let's do some simplification. So the bottom just simplifies to x cubed squared. When you take a power to a power, you multiply exponents, so that's x to the 6. We have a minus x cubed, and we have a minus 2 times 3, that's minus 6x squared. Minus times minus is plus. X squared times x is x cubed, so that's 3x cubed. So minus minus, and then the x times the 3x squared is 3x cubed. We can collect up like terms. So we have a minus x cubed and a plus 3x cubed. That's 2x cubed minus 6x squared. And to make my own life a little bit simpler later, I am going to simplify this a little bit right now. I'm going to factor out an x squared from the top, leaving me with a 2x in the first term and a minus 6 in the second term, all over x to the 6th. I can cancel these x squareds with 2 of these, making that a 4. So I have a 2x minus 6 all over x to the 4th. So I'm getting ready to build a sign chart for my second derivative. And let's set the second derivative equal to 0. A fraction is equal to 0, where the top's equal to 0, so 2x minus 6 equals 0. So 2x equals 6, x equals 3. So we have a 0 at x equals 3. And a fraction is undefined, where the bottom equals 0. So that's just x to the 4th equals 0. And that only happens if x is equal to 0. So it's undefined again at x equals 0, which we knew it would be. If the first derivative is undefined there, the second derivative is going to be undefined there. And since the original function is undefined at x equals 0, the first derivative has to be undefined at x equals 0. So that, again, breaks the real number line up into 3 parts. The part to the left of 0, the part between 0 and 3, and the part to the right of 3. Let me plug some numbers into f double prime. I'll pick a point to the left of 0. How about -1? Again, everything goes into f double prime now that we're doing a sign chart for f double prime, just like everything went into f prime when we're doing a sign chart for f prime. So let's see. 2 times -1 minus 6 over -1 to the 4th power. You can see the top is negative and the bottom is positive. So that's definitely less than 0. So it comes out negative over here. If I plug in f, let me pick a point between 1 and 3. How about 1? I end up with 2 times 1 minus 6 all over 1 to the 4th. Again, the top is negative and the bottom is positive. So that's definitely less than 0 again. Minus, 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 minus. And if I were to plug 4 in, you'd see I would end up with a positive number. So it's positive over here. This is our second derivative, so we don't put up and down arrows over our second derivative. Instead, we use those hill and valley marks. So minus, concave down, concave down, concave up. And again, I'm going to recopy my second derivative over here. I don't think I'm going to need it again, but just to have it on the blackboard because I'm about to erase all this. So f double prime of x equals, where to go? 2x minus 6 over x to the 4th. It's hard to believe that after all that work, these two come out relatively simply. But I'm going to get rid of all of this because I need the blackboard. So if you're still copying, feel free to pause the video as long as you want. But really, all the information I need is over here. So intervals where the function is concave up and concave down. Concave up from, looks like 3 to plus infinity. That's where it's shaped like a valley. That's what concave up means. And it's concave down on 2 sides of this place where we have a vertical asymptote. So from negative infinity to 0, and also from 0 to 3. And for points of inflection, we're looking for places where the function has a derivative and the second derivative changes sign, where it switches from concave down to concave up or vice versa. So we can see right away that this is not a point of inflection. The function is not differentiable there. It's got a u there. So it wouldn't be a point of inflection even if the concavity switched there, which it doesn't. It's concave down on both sides. But this is not as good as point of inflection. You can see that the function does have a derivative there, and the concavity switches on either side of this. So we have a point of inflection of, let's give the y value at x equals 3. We're going to need the y value on our graph later anyway, so we might as well do it now. Let's take 3 and plug it into our original function to get the y value. So y equals 3 minus 1 over 3 squared. That's 2/9. So 1/4, that's about 0.25. 2/9, that's a little bit smaller. That's about 0.22 repeating. Just to give you a feel for where those are when we finally get around to putting our graph together. Okay. E, intercepts. For our x-intercepts, we'll set y equal to 0. As usual, y is the original function. So if we set a fraction equal to 0, that means the top is equal to 0, so x minus 1 equals 0, so x equals 1. It's the only place where we cross the x-axis. And for our y-intercept, we'll set x equal to 0. So y equals 0 minus 1 over 0 squared. Divided by 0 there, that's garbage. So there's no y-intercept. And in F, find all asymptotes. So vertical asymptotes, we know if we have a rational function, we have a vertical asymptote every time the denominator equals 0 and the numerator doesn't. So the bottom equals 0 at x equals 0, and the top doesn't equal 0 there. Top equals minus 1 if we plug in x equals 0. So we have a vertical asymptote at x equals 0. So that's where the bottom equals 0. And a horizontal asymptote, we could take the limit as x goes to infinity or minus infinity for the original function, or we could just take the shortcut. We know that the degree of the numerator is smaller than the degree of the denominator. The numerator has degree 1, the denominator has degree 2. We know when the degree of the numerator is smaller than the degree of the denominator for a rational function, we do have a horizontal asymptote at height 0, y equals 0. So y equals a number, that's the equation of a horizontal line, horizontal asymptote. X equals a number, that's the equation of a vertical line. So that's the form that vertical asymptotes are always going to take. Well, I think we pretty much have all the information we need to be able to sketch a good graph. And let's go ahead and do that now. Let's put our y-axis right underneath our 0. And we'll try to get our x-axis to line up as best we can. So minus 1, 1, 2, 3, 4. I could dot in an x asymptote on top of, horizontal asymptote on top of the x-axis. It wouldn't show up very well. I could dot, a vertical asymptote on top of my y-axis. It wouldn't show up very well either. We can see the top of this curve is at 0.25 at a quarter. So let's put 0.25 right about here. So that's 1/4. So 1/2 would be up here. 1 would be way up here. Okay. Let's go ahead and see if we can sketch this thing. So from negative infinity all the way up to 0, we can see that we are decreasing, concave down, decreasing on a hill, decreasing on a hill. We're approaching the x-axis asymptotically. We have a horizontal asymptote at y equals 0, and we're approaching the y-axis asymptotically. We have a vertical asymptote at x equals 0. So decreasing on a hill, approaching this line. Basically, the curve is going to look like this over here. Oh, let's go ahead and plot these points that we know. We goes through 2 1/4. So at x equals 2, we're at height 1/4. That's the maximum. At x equals 3, we're at height 2/9, 0.22. So 0.22 is a little bit smaller than 0.25. Let me put these on here. So at x equals 2, we're at y equals 1/4, or 0.25 if you like. And at x equals 3, we're at height 2/9, or about 0.22. So those 2 points are on the curve. So from 0 all the way up to 2, increasing, concave up, approaching this line asymptotically, and we level out at this point. This is the top of a hill. So increasing on a hill, we level out at this point. Oh, I guess we know one more point on the curve. I almost forgot, because we worked out our x-intercept. We crossed the x-axis at x equals 1. So it's got to go through that point too. So let me do my best. Increasing on a hill, go through that point, level out at that point, approach this line. Increasing, hill-shaped, go through that point. That's where we cross the x-axis. That's our x-intercept. Leveling out at the top of the hill at height 1/4 at x equals 2. From 2 to 3, we're decreasing now, but still on a hill. Decreasing on a hill, we go through this point. Decreasing on a hill, going through that point. After that, we're still decreasing, but this time in a valley, and we're getting closer and closer to the x-axis. So decreasing in a valley, approaching the x-axis asymptotically. And considering we only had 3 points on this whole picture, I think we have every right to be reasonably proud of ourselves. I don't know what else somebody would want to know about the shape of the curve that's not represented by our picture. So again, we started with a rational function. We were able to figure out where it was going up and down to the right, where it was shaped like a hill, where it was shaped like a valley, points of inflection, maxima, minima, where it crosses the axes, its asymptotes. And from all that, we were able to synthesize this picture. Hopefully this is working for you, and I will see you all shortly.